root locus concept. The roots of the denominator in a transfer function of a system that we call it poles determine the general form of the transient response of that system. So for a system having a transfer function in this form, S plus P1 multiply S plus P2. How changing the position of the poles, that in this case is P1 and P2 in the S plane, change the transient response when the system is subject to an impulse, right? So root locus is concerned to the study of this relationship between the behavior of systems and the position of their roots. And this technique is used for the study of control system, and it's called the root locus method. Okay, so it's important to highlight that the root locus methodology was introduced in the 1940s by Evans and has been developed and utilized extensively in control engineering practice. So the root locus technique is a graphical method by drawing the locus of roots in the S plane, as we mentioned, as a parameter is varied. In fact, the root locus method provides an engineer with a measurement of sensitivity of the roots of the system to a variation in the parameter being considered. Later, the root locus technique may be used the great advantage in conjunction with the Roth-Horowitz criterion for stability and the Newton-Raphson method. So the root locus method provides a graphical information for the engineer, and therefore an approximate sketch can be used to obtain quality information concerning the stability and performance of the system. The locus of roots of the characteristic equation of a multi-loop system, for example, may be investigated as readily as the single loop system. If the root locations are not satisfactory, the necessary parameters adjustments often can be readily ascertained from the root locus. So the root locus as we mentioned, we need to understand that how we determine or how we calculate the roots, and as we see in stability basic principles, how the transfer function can give you two important data values, in this case the roots of the numerator that we call zeros, and the denominator that we call poles, right? So now if we consider a first order system, like this one, we have the input, we have the set point, we have a constant that's multiplying, and we have the system by itself, a process. We have the output, and we have kind of certain feedback, right? Just to relate to the feedback system. So we look at the diagram. We have the open loop transfer function of k s plus 1. Okay. So to start to work with that, we need to consider the concept of unity feedback or transfer function unity feedback that is more and less g in function of s equal to the open loop transfer function that is k over s plus 1 over 1 plus the same open loop transfer function that will be k over s plus 1. Okay. So when we have that, the denominator that is simplified as follows. This will be k over s plus 1 parentheses, sorry, plus k. So we can easily identify the denominator, that is s plus 1 plus k. Okay, and we want to calculate the root, we equate to 0. So we know that the value of the root is minus 1 plus k. So here is something very, very important, right? We have k. It can be considered as a gain in a system. And what k do is it helps us to give us an interval of values between the safety boundaries of our system. Or in this case, it helps us in a root locus, like finding the roots, or the location of the roots has the literal meaning. It gives us the trajectory of the roots that the system is following, but also when we as engineers analyze the roots, it will tell you which roots are not adequate for the system. So in this case, which roots can give you a critically stable system, or marginally stability, or unstable system. So in this case, when we add values to k, right? When k is equal to 0, s is equal to minus 1, has this expression relate to. When k equal to 1, s is equal to minus 2. When k equal to 2, s is equal to minus 3. And we can see that we have a sequence, right? So if we put that values in a graph, The first pole, this is the imaginary axis, and this is the real axis. Okay, so when we locate the poles, when k is equal to 0, we have a pole of -1, and later when k is equal to 1, we have a pole of -2, and when k is equal to 2, we have a pole of -3. So as you see, when we start to add values to the value of k, we start to move away from the origin, from this 0 pole plot. Okay, that means that in terms of stability, this is the unstable area, this is the critical stable area, that will be the imaginary axis, and we have the stable area. So if we observe the trajectory of the how the poles appear once we change the value of k, is giving you graphical observation of what happened with the stability. So that means the higher the value of k, the more stable is the system. And this is the meaning about root locus concept, is to find the roots, or the location of the roots, or as engineers we need to find out where is the roots located, right? If the transfer function have a constant k or has a gain added to the same function, and how this gain can change the behavior of the system, has an advantage to gain stability. So I hope you enjoyed this short class based on the root locus concept. In the following classes, we will see how, when the order increase, how the root locus can help you to describe the behavior. And once we understand how to understand the behavior, we will be able to add another additional concept, that is frequency response, right? When we propose that the systems have sinusoidal input, right? So now we're working with components of frequency. And that will give us another view of how the systems behaves once we do the analysis and we start to design the parameters in order to have, specifically for this presentation, a great stability of the system. Okay, so see you next class, and I hope you enjoy this presentation.